Hello and welcome back to Wheeler Scientific. Hello and welcome back to Wheeler Scientific. To the lab, I guess. I have to make some bug spray. Bug spray works off of a chemical called DEET, which is essential to a summer evening as the smell of freshly cut grass or the sounds of cicadas in a tree. Developed by the United States Army in 1944 to protect soldiers against insect-borne diseases such as malaria. DEET is now the silent guardian of our backyard barbecues and camping trips, offering an invisible shield against the assault of mosquitoes. But what makes DEET so effective, and how does this chemical manage to deter insects without harming us humans? Today we'll explore the science behind DEET and uncover the fascinating interplay between chemistry and biology that keeps our skin bite-free and our nights under the stars peaceful. DEET's chemical name is N-Diethyl-m-toluamide, and it works by confusing the sensory receptors of insects. When applied to the skin, DEET masks the natural odors emitted by us humans, which are typically attractive to mosquitoes and other biting insects. Instead of acting as a repellent that would drive away insects, DEET essentially makes them difficult to locate us in the first place. The compound interferes with the neurons and receptors in an insect's antennae and mouthparts that detect lactic acid and carbon dioxide, both of which signal the presence of a potential host. This disruption in their sensory mechanisms leaves mosquitoes disoriented and unable to zero in on their next meal, ensuring that you can enjoy your outdoor activities without the constant buzz and bites of these pesky insects. To make some DEET, we need a few chemicals: M-toluic acid, thionyl chloride, aqueous sodium hydroxide, diethylamine, dichloromethane, hydrochloric acid, a saturated solution of sodium chloride, a drying agent, and optional column materials. To start, we need our glassware to be very dry, or any moisture will mess with our reaction. To accomplish this, we throw our clean glassware into a drying oven for about an hour above 100 degrees Celsius, after which we take it out and allow it to cool to room temperature. We set up the glassware for addition under reflux by fitting a clean, dry 100 ml round bottom flask with a Claisen adapter, placing a separatory funnel on its straight arm and attaching a reflux condenser to its bent arm. If you cannot perform this experiment under a fume hood, equip the reflux condenser with a gas trap containing dilute sodium hydroxide. Detach the reaction flask and measure 4.08 grams, 30 millimole of tylenic acid into it. Then drop in a stir bar or boiling chips to ensure even mixing during heating and to keep any bumping from occurring. Next, add 2.6 milliliters, about 36 millimole, of thionyl chloride, a chlorinating agent that will convert the M-tylenic acid into M-tylyl chloride. Reattach the flask to the reaction apparatus and heat the mixture gently under reflux for about 30 minutes at 90 degrees Celsius. During this time, the M-tylenic acid reacts with the thionyl chloride, releasing sulfur dioxide and hydrogen chloride gases, which indicates the progress of the reaction. The reaction of a carboxylic acid with thionyl chloride to form an acid chloride is a common and efficient method in organic chemistry. In this process, the carboxylic acid reacts with thionyl chloride, resulting in the formation of an acid chloride while releasing sulfur dioxide and hydrogen chloride as byproducts. The reaction begins with carboxylic acid, which initially reacts with thionyl chloride to form an intermediate complex. This involves the nucleophilic attack of the carbonyl oxygen of the carboxylic acid on the sulfur atom of the thionyl chloride. The intermediate then undergoes a rearrangement and elimination process, where it loses a molecule of sulfur dioxide and hydrogen chloride, resulting in the formation of the desired acid chloride. Thionyl chloride is chosen for this reaction because it effectively replaces the hydroxyl group in the carboxylic acid with a chlorine atom, forming the acid chloride. The byproducts sulfur dioxide and hydrogen chloride are gases, which makes them easy to remove from the reaction mixture. The reaction is typically conducted under reflux to provide the necessary energy for the reaction to proceed, and to ensure thorough mixing of the reactants. The evolution of gas during the reaction indicates progress, and it's crucial to conduct this experiment under a fume hood due to the toxic nature and corrosive nature of the byproducts. This is why it's important, if not using a fume hood, to use a sodium hydroxide gas trap. The reason we convert the carboxylic acid to an acid chloride is because they're highly reactive, due to the electron withdrawing chlorine atom. This makes the carbonyl carbon extremely electrophilic. This heightened reactivity allows acid chlorides to react readily with nucleophiles, such as amines, to form amides, which we'll do in the next step. Once the gas evolution stops, the reaction is complete. The reaction mixture is then cooled to room temperature. To make sure the reaction is complete, I perform TLC, thin layer chromatography, which is a widely used technique in organic chemistry for monitoring the progression of reactions and ensuring that the reactions have fully reacted and converted to products. In the context of our reaction, converting M-tylic acid to M-tylyl chloride, using thionyl chloride. TLC can verify that all the M-tylylic acid has reacted. To perform TLC, we start by preparing a small amount of starting reagent, M-tylylic acid, in an appropriate solvent like dichloromethane, DCM, to create a dilute solution. Then we apply small dots of this solution and the reaction solution to the TLC plate coated with silica. Placing the TLC plate into a beaker containing some more DCM, which will cause the solvent to ascend the plate by capillary action, carrying the compounds with it. Different compounds will move up the plate at different extents, based on their polarity, resulting in distinctive spots on the TLC plate. After the solvent front has moved an adequate distance, we remove the plate and visualize the spots under UV light and/or by staining. We compare the positions of the spots from the reaction mixture to the spot of pure M-tylylic acid. If the reaction is complete, the spots corresponding to M-tylylic acid should be absent or significantly reduced in intensity in the reaction mixture sample, indicating that M-tylylic acid has converted to M-tylyl chloride. The presence of new spots at different RF values would correspond to the product of M-tylyl chloride. This process ensures that all M-tylylic acid has been used up, confirming completion of the reaction. In our case, a faint streak of M-tylylic acid is still present, so I throw about 1 milliliter of thionyl chloride and let the reaction carry out for another 15 minutes at temp. After time, the reaction is complete and the reaction mixture is cooled back down to room temperature. Next, while stirring, 30 milliliters of dry dichloromethane is added via the addition funnel. Following this, prepare a solution of diethylamine in DCM. Add about 1.835 grams, 25 millimole of dimethylamine in 8 milliliters of DCM. This mixture is then transferred to the addition funnel using a few milliliters of DCM for a complete transfer. Slowly add the diethylamine to the reaction flask over the course of about 30 minutes. This controlled addition ensures the reaction proceeds steadily without becoming too vigorous. After adding all the diethylamine solution, heat and stir the reaction mixture using a water bath at 30 degrees Celsius for 30 minutes or more. The reaction occurring here is that diethylamine is replacing the chlorine we just attached. The heating step ensures that the reaction goes to completion. By the end of this period, the characteristic odor of acid chloride should be absent. Next, we add in 4 molar sodium hydroxide to destroy any acid that may be present. After completing the reaction to form N-Diethyl-m-toluamide, the next step involves purifying and extracting the compound. First, allow the reaction mixture to cool to room temperature. Once cooled, the reaction mixture is transferred to a separatory funnel, where it is then washed with 30 milliliters of 1 molar hydrochloric acid to remove any basic impurities. followed by 30 milliliters of saturated aqueous sodium chloride solution to remove any other impurities. After these washes, the dichloromethane solution is dried over a drying agent to remove any trace of water. Next, the dichloromethane is decanted into another beaker. Finally, the solvent is evaporated in a boiling water bath. This process removes any of the DCM solvent, leaving behind purified N-Diethyl-m-toluamide as a residue. These separation steps are essential to isolate the product in high purity, ready for further purification. For purification of N-Dimethyl-m-toluamide, vacuum distillation or chromatography can be used to achieve a high purity. I do enough distillation, so chromatography it is. To use chromatography, a column is prepared by packing it with glass wool at the bottom, then follows approximately 25 grams of activated alumina. Topped with a 1 centimeter layer of sand to ensure an even distribution. Then we dissolve the crude DEET in a minimal amount of hexanes, typically about 5 to 10 milliliters. Once dissolved, we then wet the column using hexanes and allow it to drain until the elutant surface approaches the top layer of the sand. Immediately then add the DEET solution to the column, using additional hexanes to rinse the flask thoroughly, and add these rinses to the column. Maintain the column's hexanes levels near the top to facilitate a consistent elution, ensuring a stable elutant level with continuous addition of hexanes as needed. DEET will appear as a yellow band as it progresses through the column, interacting with the alumina. The DEET gets stuck to alumina, allowing impurities to flow out of the column. Next, methanol is poured into the column to force the DEET out. Once the band reaches the bottom, elute until the top of the yellow band exits the column. To complete purification, evaporate the methanol from the DEET solution over a steam bath. This method ensures the isolation of highly purified N-Diethyl-m-toluamide. We got about 1.6 grams of products, but now how do we know how pure it is? In chemistry, we use analytical instruments to uncover the structure and purity of molecules. There are a lot of powerful options: IR for seeing functional groups, NMR for seeing structure. But those don't come close to how powerful GCMS is when it comes to identifying and quantifying compounds with precision and sensitivity. Gas chromatography mass spec, GCMS for short, is like the superhero of the analytical world. This technique combines the features of gas-liquid chromatography and mass spectroscopy to identify different substances within a test sample. In the GC part, the sample is vaporized and carried by an inert gas through the column with a stationary phase. As different compounds travel through the column at different rates, they separate based off of their chemical properties. Once separated, they enter the MS part, where they are ionized and fragmented. The mass spectroscoper measures the mass-to-charge ratio of these fragments, creating a unique spectra of fingerprint of each compound. This dual capacity allows GCMS to provide highly specific and accurate identification, making it an invaluable tool for complex mixtures like DEET and its intermediates. With GCMS, we can confirm not only the presence of DEET in our synthesized product, but also its purity and any potential impurities. This level of detail is crucial for ensuring the effectiveness and safety of the bug spray we've created. Now let's take our final product to the GCMS and see the results of our hard work. A small sample was taken from the beaker and transferred to a GCMS vial, where it was dissolved in some dichloromethane, after which it was loaded into the instrument and ran. After about 30 minutes, we have our data. I also ran a sample from before we did the column purification to see how they differ. In our starting crude compound, we have 3 compounds: 2-methyl-benzyl chloride, 3-methyl benzoic acid, and our desired product, DEET. Comparing that to our sample of purified compounds, we have 2 in our sample: retamide and our DEET compound. Based off this data, we have successfully produced DEET, and in high purities, almost 99.9%. We can now take our final product, dissolve it in some alcohol, and we have successfully made some bug spray. Apply this to a rag, and you're ready for outdoor activities. Welcome to Wheeler Scientific, and thanks for watching.